Yeah. Let's see. All right. So yesterday I went through the second quantization, annihilation, and creation operators. And now I'll show you how to use this to derive couple cluster theory and basically show that untruncated couple cluster is equivalent to full CI. And then after that, I'll show you some cool tricks on how to count zeros of polynomials and how to apply this to the particular CC polynomial. Okay, so the core object that we are working with in couple cluster theory is the cluster matrix or cluster operator. And that is a linear combination of so-called excitation matrices. Matrices or operators, depending on your point of preference. We write this as some factorial E, depending on the particle number. And this is defined as x mu. And I'll tell you what mu is in just a second. A AK dagger, A1 dagger, AI1, AK. Where mu comes from I. N. Okay, so the n dependence goes through to this I, and mu is basically a multi-index that keeps track of the indices that you are creating and those indices that you are annihilating in your binary string. Okay, so let's write this down. This is I of n. It's a set of all multi-indices, I little k, AI, a little k. So this is a small k, I should highlight, right? Yesterday we see the capital N for the number of electrons and a capital K for the number of spin orbitals. And now this is little k corresponding to the excitation rank. And now I impose an ordering where I say that 1 is less or equal than I1, Ik less or equal than N, so the number of electrons or the occupied orbitals. And then I have N truly smaller than A1, AK, or than capital K. All right, so this is just a construction. And what do we do with this construction? Well, we have another observation. And that is there exists a one-to-one relation between factorial En union with the identity and what we called Bn. Yeah, remember Bn, this was the set of Slater determinants. Okay. So that means for every Slater determinant that we can think of in our set B, there exists exactly one of these excitation matrices. Okay. So let's write down the proof. I take one side to be a Slater determinant of n electrons within this set of k spin orbitals, then we know that psi can be written as a sequence of creation operators acting on the vacuum. Okay, but then, well, we just define the index set I to be n without j. Okay, so now I use two kind of notations. So I use the capital letters of indices as a collection of the small indices, right? So if I take n without j, what I get is sort of the lacking occupied indices in j. So these will be the ones from which I have to excite. And then I compute a as j without n. So this will give me the virtuals that live in this index string. Okay. Well, then I can define k to be the cardinality of A is equal to the cardinality of I. And I can write psi is equal to A, oops, this is AK dagger, AA1 dagger, AI1, AI, K acting on my particular reference state. Okay, so the reference state, phi 0, is equal to AN dagger. A1. Okay. So really what these excitation matrices do is they map you from a given reference state, which is fixed in couple cluster theory, right? So this is a Hartree-Fock approximation, or in principle could be any single slated determinant. But the excitation matrices allow you to go from this reference to all the other references. And then we can define the multi-index if we want. Let's do this. So this guy we call x mu, and mu is equal to, using this shorthand notation, IA. Okay. Now, so there's one small catch so far, right? So we have again a binary string, and we are just replacing indices. But remember that these AI1 and or AII and AIA, they had a Pauli Z matrix incorporated. So what might happen here is that you actually pick up a sign. Okay. So it's a one-to-one relation, but you don't necessarily get the particular slated determinant that you want, but you get it up to a sign. And signs in our expressibility, they don't really matter. That's why I'm a bit loose with them. Because if we form a basis, if one is pointing up or pointing down, you still get the correct space. Okay. And so then, so this allows us to freely switch between the picture of having basis vectors to having matrices that define these basis vectors by simply applying these excitation matrices to one particular reference. You'll see in a second how this becomes important, but for now we just take a mental note on this. Yeah.
Sorry. You're saying that the coordinate of A is the same as the coordinate of I?
Yes.
Is the number of elements in the set?
So this is, yes, this is, so here you have n without I. So these are the occupieds which you will excite. And these are the ones, the virtuals into which you excite. So they have to be the same. Yeah. So this is, I think, unconventional notation for chemistry, but it's, yeah. Okay. So then, so the excitation operators, they commute. This is observation number 2. Yeah, we can also prove this or convince ourselves of this. So let's just pick 2 excitation matrices. So this is 1, and then let's call the other one x nu. What indices do you want to use? It's a we have L many. What is B? B1 and A, J1 to JL. Okay, so 2 excitation matrices. And then if I just apply x mu times x nu, this is AAK. Okay. So look at this, and well, ultimately we want to compare x mu times x nu with x nu times x mu. So we want to find a way that this sequence of creation and annihilation operators are comparable between the 2 products. And we note the occupied indices, they come from a different set than the virtual indices. So we have separated them. I is smaller or equal to n, and A is greater than n. So that means, remember the car rules that we had yesterday. A P, A Q. So when we try to permute this dagger through here, the only thing that could happen is that we run into the situation, or potentially the situation, that P is equal to Q, and then we pick up a delta as commutator. But by construction of the excitation matrices, this cannot happen because BL comes from a different set than the I's. Okay, so that means when we commute this one through here, we will only pick up, well, K many minus ones. Okay. So we have -1 to the K. Yeah, actually, let me skip this intermediate step. So I think this argument is clear. I don't have to write this down. And then you can actually do this for all the other daggers too. Okay, each of them will only pick up a -1. So we get -1. For each of them, you get K -1, and there are L many of those. So K times L. And then we have AK dagger, AA1. Hmm? No, times? No, times. I get for each of them, I get K, and I have L many. I'm going to permute all of them now. Right?
Yes.
Okay. But it's good that you check because my indices, they are never, you're right. So don't trust them. AB1 dagger, A11, A1K, AJ1, AJL. Okay. Now, where to put this? So there's really no better way to write this down we have x mu minus x mu. So I'll spare putting them in right away. I'll just give you the end result when I permute the daggers through. So you can convince yourself that this is equal to k times L, AAK dagger, AA1 dagger, ABL dagger, AB1 dagger, AI1, L. Okay, this is the first term. Then you can show for the second term, you get minus from the commutator. And then we have -1, and I find 3 times KL AAK AA1 dagger AJL. Okay. So -1 to the 3 is -1. So we have -1 to the KL times this, minus -1 to the KL times this. So this equates to 0. Yeah. It's a bit of a lengthy calculation, but it does the trick. So this is how you can convince yourself that excitation matrices or operator actually commute. Okay. And then they have one more nice property that I want to give you before we go to the cluster matrices, and that is that they are nilpotent. Okay, so another observation is that excitation operators are nilpotent. Yeah. So how can we convince ourselves of this? So recall that when we write AP dagger, we have this string of Pauli Z's. And we have a dagger and then we have just identities. Yeah, and A was of this form, and AT is the transpose of this matrix. Yeah. And then, well, we note that if we take A square, we get the 0 matrix. And, well, we get the same if we take the transpose square. It's also the 0 matrix. So this in turn means that if we compute AP dagger square, or for that matter, AP square, we'll get these Pauli Z's times Pauli Z. So this will give us a bunch of identity matrices, and we get that at the pth position, A times A, or A dagger times A, which is the 0 matrix, and that throws all of this to 0. Okay. So then, so for any x mu, we get x mu square, which is a AAK dagger, which way around? I AIK times the same string, AK dagger, AA1 dagger, AI1. Okay. So now I see if I take this AAK, I can again, without any problems, permute this through here, pick up a minus sign, or like K many minus signs. And then I can push it also through the remaining K minus first ones because they were different from AK, right? So I can push this all the way through here. And I pick up K minus signs from here, K minus 1 from here. So I get 2K minus 1 minus signs. So overall, it's just a minus sign. So minus 1 AAK dagger AAK. And I really don't care about the rest because I already see that this is equal to 0. Okay. Okay, so indeed, they are nilpotent. Okay. Okay. So then maybe I can fit that here. Let me define the space of cluster matrices. Okay, so this will be the one in which we are seeking the solution. Remember, couple cluster theory made the ansatz that psi is e to the t phi 0. Okay, phi 0 is fixed. So therefore, our class of excitation matrices is fixed, and we try to find t. And now I'm going to tell you where t comes from. T comes from space that are called B, which is the span of En. So this is a set of matrices that look something like T is equal to the sum over multi-indices of our set I n. E mu x mu. And then, well, you still have 1 degree of freedom, right? And that is where these T mu's come from. So they can be either real or complex, depending on where you're optimizing over. So we can write T mu from some algebraic field where F is either R or C. Okay.
So this is not the same B as before, because we had a B of n.
Did I also call it B? Whoops. Okay. So I thought we had B of n. B of n. So if it's of n or of some integer, then it's the Slater's. And if it's just this calligraphic B, notation might be subject to approval. So.
L, I thought it was L.
Oh.
It's what it means. Yeah.
Well, this is a old German B. So we can also, or A. Yeah, call it A if we want. Yeah. No? Okay. Well, we can call it, yeah, well, I don't know. Well, let's stick to B. Yeah. Yes. Oh, is it really? Yeah. Okay. Okay. So I think I will keep referring to this as B. Let's see. Or should I pick a different? Is anything else free? Maybe that's not very valuable. Let's. Calligraphic T?
Yes.
Yeah, maybe. T matrices. Okay. All right. Let's stick to calligraphic T. Okay. So then we have a lemma. And I think this is the most algebraic that this will get. Okay, so if we have T, yeah. Mm-hmm. So yes, so F is either, yeah. I think you could do shenanigans like the F2 field or something, but we just want real or complex, right? So we no, because everything is finite in my case. So if you push this to infinite dimensions, then you have to make sure that this converges. But I hold on to the complete basis set limit. So there exists a number that might be large, but it's still finite. Yeah, I live in matrix land. Okay, so let's take T. Yeah. And equip T with the conventional matrix commutator. Oops, should write this out properly. Yeah. Equipped with the matrix commutator is a nilpotent abelian Lie algebra. Okay. So we can convince ourselves of this. So there's a few things that we have to show, right? So the first is that T with the matrix commutator is indeed a Lie algebra, but there's not much to show, right? So it's a fancy way of saying that this vector space together with this commutator fulfills the Jacobi identity, which the matrix commutator always does. Okay, so so this you get for free. Abelian, we will see, we will inherit from the excitation matrices. So we work this out. So now we can harvest our seeds, so to speak. And the nilpotency is a bit of work, but we'll also get there. Okay, so let's write this down for the Lie algebra. So we need that T is a linear space, vector space, vector space. Which is true by construction. And we need that the Jacobi identity is fulfilled. Let me just write that down for completion, in case you have not seen this before. And then recycle. So so this is called the Jacobi identity. And we need that the Jacobi identity holds. But this is also true, since we have the conventional matrix commutator. So usually for the Lie algebra, you have a linear space and you put on some Lie brackets that you define in some way, and you have to show that this is fulfilled. For us, if we just put the matrix commutator there, all of this falls into place, which is why I think this is a very nice framework for coupled cluster theory, because once you've gone through second quantization, all of these things come basically for free. So it seems like a natural thing to discuss coupled cluster theory from this perspective. Okay, so let's look at the commutator. So we have T1 commuted with T2. Well, we get the sum over mu nu T mu 1 T nu 1. We used we should get x mu x nu. So I hope I did this right. So you use linearity in the first entry and then in the second one. Okay. No? Yes, no? Yeah. Oh. 2. Yes. But linearity in entry 1 and 2. And then, well, since this guy is 0, all of them are 0. Okay. So it's a abelian. And now we want to look at the nilpotency. Actually, when did we start? I don't know until when do I have?
What is around 11?
Okay.
So I think you have, you can go to 12. 14.
Okay, we'll see if I have enough to say until then, but yeah. Okay. So the nilpotency is a bit, at least for me, it's not that easy to see. So let's recall the following multinomial theorem. So this is a Wikipedia. You find if you have m summons to the power of n, then this is the sum over k1, k little m that equates to n, where k1 km is greater or equal than 0. Then you have the multinomial coefficient n k1 km. Let me write this. And then we have the product j equal 1 m xj kj. Okay. Where n k1 km is equal to n factorial k1 factorial km factorial. Okay. Yeah, so this is the multinomial theorem for variables. So let's take a look at p to the power n plus 1, yeah, because I know it will be 0 at n plus 1. So let's look at this guy. And I can write this k1 plus km, which equates to n plus 1. All right. E mu j x mu j kj. So in this case, m is the cardinality of I. Okay. So I have T, which is a linear combination of excitation matrices, and I have m many. Right. So then I look at these numbers k1 to km. I sprinkle them over my so m is now much larger than n. Right. So lots of them will be 0, some will be 1, and in principle you could think that some of them are 2, 3, and so on. But note, kj can at most be 1. because if it's 2, this will be 0, okay? So this is sort of our first observation, that decay j are smaller or equal than 1. So they're actually, it's a binary string again. So I have a binary string of length m, which is very long, and I populate n plus 1 ones here. Okay. All right. So now the question is to you guys, does there exist a binary string such that this product is non-zero? Okay, so there's a number of kj's that are 0, so I get the 1 or the identity, but then I have n plus 1 ones. So I have n plus 1 of these x mu's. Okay. I'm not going to write down the question, actually. It's going to write this down as observation 2. Yeah. So what you need for j equal 1 to m, p mu j, x mu j, kj, for this product to be non-zero, you actually need that the intersection of all the occupied indices in these x mu, that's empty, right? So I can, let's take the single excitations, right? I take only single excitations here. And these guys are all distinct. They're all different. And I'm trying to find n plus 1 single excitations such that the occupieds are non-overlapping. But I can only pick n occupieds to begin with. So it's literally impossible to pick n plus 1 occupieds that are different out of a set of n. Yeah, make sense? Okay, let's try to write this down. Now, for this to be non-zero, we need that mu I1 intersected with mu I n plus 1 is empty. Okay, so maybe not the most mathematical, but these are multi-indices, so that means I intersect the virtuals and the occupieds. In the virtuals, that's fine because the principal k can be very, very large, but the occupieds are the ones that give us the nilpotency. Okay, so then I'm writing in words, taking n plus 1, distinct indices out of a set of n available indices is impossible. Okay. Yeah.
Just a question about
Oh, what I erased. Okay.
I don't understand why you speak about the algebra.
Yeah.
Whereas all the brackets are 0, so there are no algebra structure. And you are looking at the nilpotency respective to the matrix products instead of the nilpotency respective to the bracket.
So first of all, the Lie algebra structure is trivial, right? Because all the commutators vanish. So it is, I mean, it's, how to say? Well, it's not, from the algebraic perspective, this is probably not the most interesting case to look at. But coupled cluster very naturally fulfills this trivial structure. Yeah, and we will use this later to talk about the exponential, and that you get actually a bijective exponential map between this Lie algebra and the corresponding Lie group, which means couple cluster is equivalent to full CI. This is the idea. So although this is not super fancy, it does the trick for us. Yeah, and then what was question number 2?
Not the Lie bracket point.
That's right. Yeah, that's right. Yeah. Yeah. What was I saying? Yeah, this finished it. Yeah. So then so the question now becomes, what's the corresponding Lie group? Okay. So again, from the algebra, this is not fancy, but we want something very specifically for a couple cluster theory, right? We want that the exponential of t. Okay, I'm not going to spoil what we want. Let's stick to the script, okay? So let's try to work this out. Okay. So let's pick a psi which lives in our n-particle sector of the Fock space. With psi 0 is 1. So it's intermediately normalized with respect to our reference. Okay. Then we can write psi is equal to phi 0 plus some linear combination of excited Slater determinants. But we've seen that there is a one-to-one correspondence between these guys and excitation matrices. Yeah. Phi 0, yeah, so we can just factorize phi 0. So then really what we are interested in is, because now we work with these T's, yeah, we formed an algebra, although trivial, but we work with these matrices, and we want to say that any vector that is intermediately normalized can be expressed through these matrices. This is basically what this line tells you. Okay, so we are looking at the map omega. Omega goes from T into some set G, and it maps a matrix C to identity plus C. Okay, so again, this is not fancy math. It's very simple, yeah, but it does the trick for couple cluster theory. Yeah. Yeah, so by construction, this map is surjective, but also since these coefficients are unique, this map uniquely describes any state that is intermediately normalized. Okay, so for any state that looks like this, we can define a unique operator that maps the reference to this guy, and vice versa. Any operator defines. Okay. Yeah, so this we could convince us that this is true easily, and I will just use this as an intermediate step for showing that CC theory is equivalent to full CI. Okay. So the set that is of interest to us is the set of exponential t's, okay? So this here, since we know that the t's are nilpotent, one, and you know, we know this truncates. You know? So in particular, it's well defined. We don't have to care about series convergence of this matrix exponential. You know? And then what we want to show, which is another observation. And that's that G is equal to G tilde. Okay. So I introduced G tilde, or G, sorry, I introduced G as a very simple set just to make sure that you see any psi that is intermediately normalized can be written as an operator times the reference state. Okay. So now if we show that G tilde is equal to G, that means in turn that any state that is intermediately normalized can be written as exponential t, where t comes out of our set of cluster matrices. Yeah. Okay. Yeah. Yeah.
So if you were doing unitary couplet cluster instead of,
Yeah.
so this exponential series would not truncate, right?
That's correct.
So can you still show that unitary couplet cluster is equivalent to full CI?
So don't get me started on that one, because I think so. I think it's true, and it's I mean, this is recorded now, so but this is an ongoing conjecture between in a small circle.
All right.
So I'm very happy. I would love to share this with you afterwards.
Okay.
But it's a very intriguing conjecture. It's like actually a bit more general than UCC. But it seems to be true, but I can't prove it. People have tried, they didn't manage, but we're still working on it. Yeah, yeah. But good remark. Thank you. Okay, so we do this by inclusion. Oops. Yeah. First look at this one. So let t be in T. Then, well, clearly exponential t is identity plus some polynomial of degree n of t. Yeah. Where p yeah. But tau is a vector space. So, well, P of t is also in T, right? So what we have is that x of t is equal to I plus some matrix C with C in T. Yeah, so, well, this is true. No? So this is the one way. Let's look at the other way. So we look at I plus C in G. And well, since C is in tau, we know that this is also nilpotent. So what we can do is we can look at the logarithm. We look at the logarithm of I plus C. And then again, you open Wikipedia. And this tells you this is -1 to the n over n plus 1 Cn plus 1, or maybe some series expansion like this. But you know that C is in tau or in t. So this also terminates after well, n terms. Yeah? So this also terminates. So in particular, log is well defined. And this is some linear combination of a matrix C, where C is in T. So in particular, it's also in T, because it's a linear space, right? So any linear combination is in there. So what we can do is we get that I plus C is equal to exponential of the logarithm of I plus C, where we have convinced ourselves that this guy is well defined and lives in T. But this thing, this expression, lives in G tilde, right? So we've taken an element and have shown that this lives in G tilde. Yeah.
Okay, good. But what is the difference between the T and graphic T?
So calligraphic T was the space of cluster matrices, where we convinced like this was the notation we then picked. Yeah.
Okay, the above one?
It's the same. Yeah.
Okay.
So that's the result, right? So I plus C. Yeah. So T was the space of linear combination of excitation matrices. So I plus C is not in T. Yeah, because you have identity. But you take the logarithm, and this is a linear combination of the matrix C, where C comes from T. So the linear combination lives again in T. So the logarithm I plus C is indeed in calligraphic T. Okay. But these are the same. Okay. Yeah. Okay. So we're done. And so this shows that we can freely switch between linear expansion if we have intermediately normalization and the exponential formulation. Yeah. So maybe a concluding remark on this first part. Yeah. So this shows that the CC ansatz is in quotation marks well defined in the sense that you reach a very large portion of your Hilbert space. So you don't reach anything that is orthogonal to your reference. That's just impossible with an exponential. But as long as you have intermediately normalization, or in fact, any overlap with your reference, you can, with pen and paper, argue that you reach any state. Okay. All right, so this is what I wanted to say about couple cluster theory or the CC ansatz. compared to configuration interaction. And now let's talk about counting roots of polynomials. Okay. Counting roots of CC. So if we try to count the roots for a general couple cluster theory, this is rather ambitious. So let's be reasonable and let's try to compute the roots corresponding to CCSD. So what are the CCSD equations? There's basically two different kinds. So we have a single excitation this one to be 0. We have okay, so we want to find zeros to these sets of equations. So in this notation, just to reiterate, we replace the index I in the reference with A, and here we replace the indices I and J in the reference with A and B. Okay. And we've seen yesterday that this expression is a polynomial in T of at most order 4, regardless of the truncation. Okay. So we can go ahead and establish our very first but naive bound. And this comes from Bézout's theorem, which says that the number of roots of a polynomial system is bound from above by the product of the degrees of the individual polynomials. Okay. So maybe I should write this down. Huh? Now the number of roots to a, in fact, it's a generic. Bound by the product of the degrees of the polynomials. Okay. So in order to apply this, we have to answer the question, how many equations are there? Okay, so let's look at the singles equations first. So I can pick any orbital in the occupied space. So I have n options for I. And I can pick any A in the virtual space. So that's k minus n. Okay. So for the number of singles equations is n times k minus n. Okay. Well, for the doubles, I can place 2 indices on n slots without caring about the order. and that we know that's the binomial distribution. So this is n, choose 2, and here we have k minus n. Choose 2, right? So our very first bound, so the number of roots is smaller or equal than 4 to the ns and d. Okay. Lots of numbers, right? So let's put some life into this. Let's do something simple. Let's pick n equal 4. So 4 electrons in 8 spin orbitals. So in this case, we have ns is 16, nd is 36. So we find n roots is smaller or equal than 4 to the 16 plus 36, which is approximately 2 times 10 to the 31. Okay. So that's absurd, right? I mean, if you think about this matrix, even in second quantization, right? If you do a full CI, that's 2 to the 8. Yeah, and this bound is just like grossly overestimating what's going on. In fact, for such a system with a very specific Hamiltonian H, we could compute all the roots. Yeah. So compare. Okay, so this is not for a generic system, but this is for a very specific Hamiltonian. We've computed this to be equal to 16,000. Okay. So what's this? Well, maybe 27 orders of magnitudes off. Yeah. So that's terrible. Okay. So let's try to make this better. Yeah. So the first thing that you will hear the pushback from is that, well, I in this case assumed that all of the polynomials are of fourth order. But you can easily show that this is not the case. And so in fact, only here you have fourth order. These single projections will be of lower order. So let's look at this. So this is sort of our one improvement. Yeah, sounds fancy, but keep in mind, I mean, we have what's the 26 orders of magnitude to go. So this will not get us very far, but it will get us somewhere. Okay, so if we have phi ia e to the minus t, this really just has two contributions because it's the exponential t. So it's an excitation matrix acting to the left. It's a de-excitation. Okay, so you have an identity part that recovers phi ia. But then, well, we check in T. Is in T any element that, when acting to the left, moves A down to I? And there's exactly one element that does that, which is xia. So you get plus TIA. Whoops. Phi 0. Okay. So the bra in this equation here. So let's if you think of e to the minus t acting on the phi a to be the bra and e to the t to be the ket, and the bra has only first order excitation or no excitation. For the Hamiltonian is a two-body operator, right? So it can only correct up to 2 excitations of difference. This is related to the Slater-Condon rules. So the biggest state that can be in the ket can only be a double excitation away from this guy, which is a triply excited state. Makes sense? So let's write this down. Since H is a two-body operator, ket must not be more than two excitations. Away from phi IA. And since we are acting on the reference, the only option that we have for this is that the e to the t will only contribute with the linear part, sorry, the constant part, the linear part, the quadratic, and the cubic part. Yeah. So only identity plus t plus 1/2 t squared plus 1/6 t to the cube applied to phi 0 will contribute. Okay. So it's at most cubic. So this will give us the defined Bézier bound that states that the number of roots is bound by 3 to the ns times 4 to the nd. Okay. So again, lots of numbers. Let's go back to our 4, 4, and 8. N equal 4. K is equal to 8. And we get that n roots is smaller or equal than 3 to the 16 times 4, 36, which is roughly 10 to the 28. Okay. We got 3 orders of magnitude, but we're still very, very far off. Yeah. So as a spoiler, right? I will not be able to get down here. Yeah, we can get a bit further, and I will motivate this, but it's pretty hard to get this. Mhm. Okay. So now I will show you something that we tried, which unfortunately didn't work very well. So there's a catch in the end, but it's a really cool trick to count the number of roots. Okay. Yeah.
That you wrote down, you get counting complex.
Yeah.
As well.
Complex. Yeah.
And this means the number of distinct groups.
Yeah. 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 Okay, so can we do better? And then you go into one of these books that talk about polynomial systems and how you can solve them. And you see that Béziers theorem is sort of the roughest, but if your polynomial system is particularly sparse, which the couple cluster one is, there are better options available. Okay. And our candidate here, our fighter, is the Bernstein Bowanski. Kushnirenko, or for obvious reasons, BKK. Theorem, okay? So this has a nice closed mathematical formulation, but I think it would be more instructive to show on an example what this theorem tells you. Okay, so let's do this. So we have a system of polynomial equations, and let's pick them bivariant. So we have f of x, which is a, 1 plus I want a2x plus a3xy plus a4y, and I have another one. b1 plus b2 x squared y plus b3 xy squared. Okay, so this is my system of polynomial equations. Okay, and then there are some analytical ways that you could use to find that for generic coefficients, this system has 4 distinct roots. Okay, so I'm not going to compute this, but you can find this calculation in Sturmfeld's solving systems of polynomial equations. Yeah. They compute the discriminant and all that stuff. Yeah.
So what do you mean by sparse linear system?
So this is bivariant. Let's look at this one. It's bivariant, and the degree is 3. But you look at all order 3 monomials, or up to order 3. So you have a constant. We have the constant. But in this case, the coefficient for xy is 0. Also for x cubed and y cubed is 0. So you're looking at all possible monomials of your polynomial system and look at how many of the coefficients are 0.
Matrix representation of your polynomial equation.
Correct.
Meaning the matrix is sparse.
Correct. And I think that's the case for coupled cluster theory because you have so many variables. Yeah. Okay. Okay, so four roots. That's the goal for today, yeah, or for the last 15 minutes. Yeah. I have some more to say. Let's see. So yeah. So first, let's compare Besut. Yeah. So this is 3, this is 2. So says 6, right? So we're 2 off. 2 might not seem like such a big deal, but we've seen for coupled cluster it's has a huge impact. Now, the game of the BKK theorem is the following. We write down our polynomial in its monomial basis. So we have f of x comma y is a1 x0 y0 plus a 2 x to the power 1 y to the power 0 plus a3 x to the power 1 y to the power 1 plus a4 x to the power 0 y to the power 1. Now each monomial now corresponds to a point in a space of dimensions of the number of variables. So 2 dimensions. So each monomial will correspond to a point in 2D. Yeah. So here we have 0, 0. This is our point 0, 0. We have 1, 0, so it'd be the point 1, 0. We have 1, 1, and we have 0, 1. Right? So this is the game, right? We write down the polynomial in monomial basis, and we get points. Now, what happens when we take the convex hull of these 4 points? Well, in this case, we get a square, or something that looks close to a square. Yeah. Yeah. So these guys, let's call this one P, which correspond to F. These are bodies of this construction are so-called Newton polytopes. Yeah, so for every polynomial in our system, we can construct one of these Newton polytopes. Let's do the other one for H. H of xy, b1 x0 y0 plus b2 x2 y1 b3 x1 y2. Okay, so we get the points 0, 0, 2, 1, and 1, 2. So we get this point, and roughly this point, and roughly this point. Let's call this Q. So for every polynomial in our system, we form these geometric bodies. And then BKK theorem tells us that the number of roots bounded from above by the area of P plus Q. Okay, so I just write it down for the case of 2. Minus the area of P minus the area of Q. This is pretty surprising, right? So we have a polynomial system, some algebraic construction. We form geometric bodies. And now we compute the volumes of them. And this gives us a bound. Okay. So maybe I should say a few words about P plus Q. Yeah. So this is called the mixed volume of the Newton polytopes. Yeah. So if you then go ahead, and I mean these are 2-dimensional ones, you can figure this out, how big these things are. You'll find that the mixed volume is 13/2 minus 1 minus 3/2, which is 4. Okay. So this is quite surprising, right? So we have Bezout's theorem, which is pretty rough. It overestimates, yeah. And now we have this pretty cool geometric constructions, which find the right root. Yeah.
I think you find the area of P plus Q isn't the volume.
Okay, let me make a picture. So this is Q, and P is somewhere here. So The set description is you take any P in P and any Q in Q and just add these vectors together. So you take this square and you can think about having this slice of pizza, which is Q, and this is the anchor point. The orientation remains the same, but you move this anchor point along this square. This is basically what this is telling you. So the mixed volume will look something like this. You have the square, and then you have the pizza that goes up here, something like this, and then you shift it over. It goes down here, and then you move it down. Yeah. So it'll look something like this. Yeah, P plus Q. Yeah. To just add all the vectors in these two sets. Oops. So this is pretty exciting, right? And there's also software that uses this. So you can go ahead and check for small systems. How does the BKK bound perform for a couple cluster? And now we went smaller. N equal 2, K equal 4. And we have our naive Bezout was 10 to the 24. Then the improved Bezout with taking into account that the singles equations are only of order 3 gives you 324. And if you go ahead and actually implement the BKK bound or compute the BKK bound for this kind of system, you find 50. Yeah, which for a generic system of CC equations of that size is sharp. Yeah. So this is pretty cool, and we got really excited. And we were wondering, can we generalize this? But there's of course a catch. Yeah. Any ideas what the catch could be? Yeah.
The volume of answering tests in high dimensions.
That's correct. So you have to compute these extremely high dimensional Newton polytopes. They are highly structured. Yeah, so when you look at them, their formulas, you see that there is something going on, but we were not able to capture the structure well enough so we could push this this bound to higher systems. Yeah, so these were brute forced. Yeah, so there's software like Vertini that can do these calculations for you. Yeah.
So we're not able to calculate the volume, or
Yeah, not efficiently. Yeah, so if you pass this on to software, they scale, I think, exponentially. So we talked to the people in Polymake. They said, yes, this is where there's no free lunch, right?
Okay.
So this is where the exponential dimension comes in. Yeah.
And I have another question for the first example on the left. I mean, the example on the left.
This one?
No, on the left. What is the exact number of?
Yeah, 50. So this for yes, for generic, yeah. If you have a specific Hamiltonian, this number will go down. But for generic coefficients, BKK actually is sharp. So there is sparsity that this level of theory captures, but it's still inaccessible. You know? So the catch is, well, you have to compute the volumes. Yeah.
For fixed n, for example, or a fixed scale or fixed n and you increase scale.
Yeah.
Do you have any idea how fast the number of solution increased? Exponential.
So we've done this in another work. I do not know the numbers off the top of my head, but I can look them up for you. So we have made a table for exactly this case, fix n equal 2, and you increase k, and these numbers go up quite aggressively. So we didn't do this with BKK because the computations are so heavy, but we have established another type of bound, which I will maybe motivate over the last 5 minutes how it works, that was able to push calculations at least a hair further. So we can do a little bigger. Okay, so yeah, what I want to say here is BKK is a pretty cool theorem, right? So that's a pretty neat trick if you want to compute the bound. I mean, in low dimensions, you can compute these volumes and get an idea of how many roots there are. But for couple cluster theory, so far there's no, how to say, no description, no fast description of the Newton polytopes. So what does work and what does give you significantly better bounds than Besut in the experiments is an alternative bound. Okay. Okay, and I will just, so there's not enough time to go through the details, but I want to motivate where this bound is coming from. Okay, so let me first state it. So we have something that's called CC degree. Okay, so this is the number of roots for a generic couple cluster system of equations corresponding to k spin orbitals and n electrons. And of course, it also depends on the level of truncation, sigma. In our case, let's make an example. E.g., sigma looks something like 1, 2 for singles and doubles, 2 for doubles, 3 for triples, 1, 2, 3 for single, double, triple, and so on. Okay. So this is generic. So this will still overestimate the number of roots compared to a true chemical system, but it's a pretty good bound. Or this is sort of the ground truth. And the bound comes now. So the bound is given by the dimension of something that we call V sigma plus 1 times the degree of V sigma. Okay. So V sigma are what we call the truncation varieties. Okay. So when talking to real algebraic geometers, they look for varieties everywhere, and you find them in couple cluster theory almost everywhere. So what is a variety? Let's make a very simple example. Let's look at S. So these are our T amplitudes that live in whatever algebraic field we have, R or C. And M is again the number of excitation matrices that we include. And then we seek to minimize or to find roots to this set of equations. And this already defines a variety. An algebraic variety is defined through an algebraic expression equal to 0, a polynomial equal to 0. It's a 0 set, basically. Yeah. Make a little fancier example. So let's look at Px, yz. So this is P1, x squared plus y squared minus z squared, and P2 x minus y over square root of 2 plus z minus 1. This equation, if we set this to 0, looks familiar to the one or the other. If you haven't seen this, this is a cone. So the 0 set of P1 looks like this. And the 0 set of this equation is a plane. And the orientation of the plane is very carefully chosen such that it lies in a three-dimensional space in a way that it intersects with our cone along like a parabolic curve, right? So these are cone cuts. Yeah, you might have seen those in physics. So the set of simultaneous roots is given by this curve. Yeah. That's the red curve. And this is our variety. Yeah. So variety is nothing fancy, but it has a number of properties. Right? So it has a dimension. So a variety has a few properties. And I only care about two, dimension and the degree. So the dimension, well, dimension is relatively clear if it's sort of connected. This case, it's 1D, it's a curve. If we only look at this set, yeah, it's 2D, it's the plane. And the cone, well, also 2D, right? So dimension is, in quotation marks, self-explanatory. So there are some tricks, but in the case of couple cluster theory, let me tell you, this quantity is very easily accessible. The troublemaker for us is this guy, it's the degree. So the degree of a variety is the number of intersection points with the generic plane in the complex sense. In the real sense, yeah, to assume these are real, then it's the maximal number of intersection points with an arbitrary plane. Since we have a 1D curve, how many maximal intersection points can we have with the plane? 2, right? So the degree of this particular variety is 2. So the degree is the number of is the maximal points, yeah. And so the plane has to be of dimension, has to be of the codimension of the dimension of the variety. So here in our case, variety was 1-dimensional, codimension is 2, so it's actually a plane. If we have some other scenario, we always have to intersect with the codimension, with the plane of dimension of the codimension of the variety. Yeah? Plane with, well, getting lazy. So right, a dimension of plane is equal codim of the variety. And this is in general very hard. You know? Intersection theory is a big field of research in pure math, as far as I know, as people have told me. So the troublemaker for us is really this guy. For certain couple cluster versions, these truncation varieties turn out to be very well studied mathematically. So the Grassmannian arises, that is very well understood algebraically. Other versions arise that people know, but a lot of them we actually don't know. And this is sort of a small goodie or getaway present, yeah, that this is still ongoing research. And if you're interested in this, feel free to join the endeavor. It's a good point to stop. Oh. Any questions, please?